Hey there, Mustangs. Back with another edition of fun math stuff here for you guys. I just realized with this on here, like, holy cow, my head is so shiny right now. It's fantastic. I mean, like, look at that. I am glowing, people. I am glowing. So today in this lesson, what we're going to be doing is we're going to be talking about complex numbers and then how to write answers in standard form and how to do just basic operations with complex numbers. Before I get into that, I did want to talk to you guys about just like a brief history of complex numbers, where they come from, because people are always like, "Why do we have these? These are stupid," you know. And they complex numbers had a long road to actually get to where they are. And the whole idea is that when we're working with problems, when you have a degree in a problem, so let's say the degree is two, a two for the degree tells you that there's supposed to be two answers. If there's a three, it tells you there's supposed to be three answers. If there's four, there's supposed to be four answers, and so on and so forth. So this goes all the way back to, believe it or not, the 16th century. When we go back in time to the 16th century, there was a mathematician that went by the name, well, his name was Cardano. And he was an Italian mathematician that basically what happened was he was encountering square roots that had negative numbers while he was working with cubic equations. And he described his book called Ars Magna. I don't know if I'm saying that right. I don't speak Italian. But he said he treated those numbers as suspicious numbers, and he called them actually sophistic in his actual book. So then, fast forward, there was another mathematician, Raphael Bombelli, and Bombelli was also an Italian mathematician. He credited the first systemic treatment of the imaginary numbers in his work in a book called Algebra. Shockingly, right? This was back in like 1572. And what he did was he introduced the idea to handle solutions for cubic equations through using Cardano's method, and that it sometimes involved square roots that were negative. But the final solution, it was even when the final solution was real. So then, fast forward even further, there's three more mathematicians that were still involved in this entire process for complex numbers to come about. Rene Descartes, who was actually a French philosopher and mathematician, he actually was the one that we give credit to for coining the term imaginary back in 1637 in a book that he called Les Géométries. That's my French. I don't know if I'm close or not. He used it when he said it, it was actually in a derogatory way. So it was like Les Géométries. And he said it was he basically had skepticism, excuse me, about the use of this number and if it actually should be applied. So he gave it the word imaginary. So then the next mathematician from there was Leonard Euler. Now, he was the one, and he's actually a famous mathematician that does a lot of calculus stuff that you guys are going to learn next year. But he formalized the concept by introducing the notion that when you have three i's in a row, it was actually the square root of negative one, negative one, negative one. He came up with this whole concept in the 18th century, and he explored this further. And then we get down to finally Carl Friedrich Gauss. And Gauss is another famous mathematician. If you ever studied matrices, you know about Gaussian elimination. And he developed the theory of complex numbers and created what's known now as the fundamental theorem of algebra, which incorporates this imaginary stuff. So complex numbers are really not that complicated. It's just that we use them when we're talking about solutions. But there's a form that we use, a standard form, and it's the form a plus bi, where we have the real part as the a, and then the imaginary part as the b portion, and it always goes in that order, a plus bi. You shouldn't have the I first. You always go a plus bi. So when we're looking at a problem like this, we've got 3 plus 3i plus 8 minus 2i minus 7. These go together based off of if they have i's or don't have i's. So the parts that have the i's here, we're going to throw those together first. Okay. So the 3, the 8, the minus 7, those all go together first. And that means that we're going to have 11 minus 7, which is 4. And then the second part of this, the 3i and the minus 2i, is simply going to equal positive 1i or just I. You can use the 1 or the I or just I, it doesn't matter. Okay? That's it. That's the whole thing. You got a plus bi there. When we look at a problem like number 2 and you're doing multiplication with these, you still multiply just like you would when you have binomial times a binomial. So when we're doing this, just go through and multiply like you normally would, your little whole FOIL method. I call it the moon method because it looks like a moon. But we multiply this out, we're going to end up with negative 56, positive 21i, positive 48i, and then we have minus 18i squared. Okay, that negative 56 is good, that 69i is good. This one right here that we have to talk about. It's important to note that I squared, if you recall, is the same as a negative 1. So what this actually says is we have negative 18 times negative 1. And so what that turns into is a positive 18. So if we continue and put things together, we have negative 56, okay, plus 18 plus 69i, okay? And we could just go ahead and throw those together. And we have, what is that, negative 38 plus 69i, right? 56 minus 18. I'm sorry, I'm having a brain fart. I just finished lunch and my brain is just not with me. Yeah, negative 38 plus 69i. There you go. I was right. All right, so that would be the answer on that one. Number 3, when we see a squaring here, there's a shortcut I want you guys to try to start getting used to whenever you see a binomial squared. And it's real simple. You just square the first term, square the second term, and then multiply the two and double them. So if I square this first term, it's a 1. If I square this term, it's a 49i squared. And if I multiply these two together, it's a negative 7i. But if I double it, it's a negative 14i. Square the first, square the last, and double the middle. Okay. This turns into a minus 49. And we've already got a 1 in the front there. So put those together, we get negative 48 minus 14i. That's it. All right, take a look at number 4. When simplifying this, you have to use a conjugate. You should remember this from Algebra 2 when you guys did this, but the conjugate is always the opposite of the denominator. That's the conjugate, but using the same terms. Now, the reason we do this, so we're going to use a 4 and a 3i, but we're going to use the opposite sign, is what's going to happen is this is going to actually get rid of the imaginary part in our denominator, okay? So if I multiply out this top part, we're going to have 20 minus 15i. Nothing to do with that. We're done. But for the denominator, multiply it out. And what's going to happen is we're going to have 4 plus 3i times 4 minus 3i. And we're going to do 16 minus 12i plus 12i and then minus 9i squared. So every time you're using the conjugate, what's supposed to happen is that these middle terms will actually eliminate themselves. Okay? And so basically what I do is I just generally don't even think about them. I just take the 4 and the 3 and square those and just always add them together. The reason we always add them together is because this minus 9i squared that we have right there is going to turn into a plus. So it just becomes 16 plus 9, which will be 25. So generally, as I said, I kind of skip some of the work and I say, well, 4 squared and 3 squared, that's 16 and 9, it's just 25 for the denominator. Now to put in the standard a plus bi form, we have to break our fraction up. So that's going to be 20 over 25 minus 15 over 25i. Okay? Simplify those fractions. We could divide everything by 5 for the first part. We have 4 over 5 minus 3 over 5i. That's your a plus bi form. Okay? 2 more things I want to do with you is completing the square and quadratic formula. So I want to show you what this actually looks like and why we have imaginary answers, okay? So this square that we see right here tells us that there's supposed to be 2 answers for this problem. And what happens is when I look at the graph of this, okay, I went ahead and put this in. X squared plus 4x plus 10, when we look at this, you can see that that graph right there is actually sitting above the x-axis. If there were 2 answers, this is supposed to hit the x-axis twice, but it doesn't hit the x-axis at all. And so because we don't have any answers that hit the x-axis, we don't have any real answers. But what we do have then are the imaginary answers, okay? And so what's going to happen is we're going to work through this, get those 2 answers, but they're going to be imaginary solutions. So here's the first method, completing the square. X squared plus 4x plus 10. Think back to what we did last time when we were completing the square. I'm going to move the 10 over, and we get negative 10. I'm going to complete the square by taking half of 4, which is 2, and square that, which is 4. And I'm going to add that to both sides. This becomes x plus 2 squared. That's a negative 6. We take the square root of both sides, and we get x plus 2, And right here, what's going to end up happening is we're going to end up with the square root of 6 and then an I. I can't take the square root of a negative. This is where we get an issue, an error in our calculator. So we just leave it as an I on the outside, making it imaginary. And then we have x equals -2 plus or minus, sorry, I forgot the plus and minus there, root 6I. These are the two answers. There's technically no big or small, but what I did was for our key, I went ahead and said it's -2 minus root 6I is the smaller one. I don't know, just more negatives. And then -2 plus root 6I was the bigger one. If you were to do the quadratic formula with this, same thing. Your A value equals 1, your B value equals 4, your C value equals 10. Let's go ahead and just simplify that. So we get x equals -b plus or minus the square root of b squared minus 4 times ac all over 2 times a. Hey! So there's your quadratic formula. That's the Notre Dame fight song if you guys don't know it. And what we're going to do is we're going to go ahead and throw the a, b, and c values in there. So we get opposite of 4 plus or minus the square root b squared minus 4 times a times c all over 2 times a, which is 2 times 1. We get x equals -4 plus or minus the square root of, this is 16 minus 40 divided by 2. Okay. And now we have x equals -4 plus or minus the square root of, what is that? -24 over 2. This will be x equals -4 plus or minus. Now 24 can be broken up into 4 and 6. Okay. And then we got the -1 in there because it's a -24. So if I take the square root of 4, that's going to equal 2. Square root of 6 will stay the way it is, and then the -1 just becomes an I on the outside, and divide that by 2. So if we break each one of these up into their separate parts, this is one fraction, and then this is one fraction, so there's 2 separate fractions there. That becomes a -2. Let me erase that. A -2, and then plus or minus, and then the 2 divided by 2 will reduce, and we're left with square root of 6I. And you can see that matches the same answer we just got on the previous problem. Okay. Hope this is clear. They're really not that complex, but if you have any questions, please let me know. Don't forget to like and subscribe. No hair, no problem. We got plenty of things to go on our head for this year. You take care and have a wonderful day.